Okay, so in this video we'd like to talk a little bit more about looking initially at the optical pumping and getting ready to take data. So what we have going on here, as you can tell, is the horizontal sweep is turned on, and as we mentioned, we use the recorder output, which is proportional to the magnetic field in the horizontal coil on the x-axis, and the amount of signal received at the photodetector on the y-axis. And we have the oscilloscope here set in XY mode. What that does is it forces the X voltage to map itself this way on the oscilloscope and the Y voltage to map itself this way on the oscilloscope. So we know you're used to oscilloscopes as always being voltage versus time, but in XY mode we can sort of assign any voltage to the X-axis and any voltage to the Y-axis. So the voltage in this axis here is proportional to the magnetic field sweep magnitude on that recorder output discussed earlier. So this is thought of as magnetic field strength in the horizontal Helmholtz coil. This is the photodetector output on this axis. So we're really looking at horizontal Helmholtz coil field versus intensity of light hitting the photodetector. That's what this is here. And as you can see, it's slowly sweeping across. This is the magnetic field that we discussed. And what I'd like to show you in particular is this big dip right here. So for some reason, at a particular magnetic field sweep value, very little light makes it to the photodetector. Where would that light be going? Well, it's being absorbed by the rubidium atoms, and that's sort of the thing about how optical pumping works is suddenly there's very little light hitting the rubidium atoms, and there's some physics in there describing why that happens. And as the magnetic field sweeps along, the light that hits the photodetector rises again to some maximum level, and it sort of ends the sweep. The sweep bounds is hit, and then it goes back and repeats again. So it turns out that this peak here is an indicator that we have found zero magnetic field for the rubidium atoms. So the sweep field is canceling the horizontal Earth's magnetic field at some point, and then the vertical magnetic field, which as you know is controlled by this knob here, is doing its job canceling the vertical component of the Earth's magnetic field. So what I'd like to show you is what happens when we turn this vertical magnetic field knob a little bit here. Watch what happens to this dip. So I just turned it a little bit. See how it's getting a little wider now? That means we're not doing such a good job at canceling the Earth's magnetic field anymore, so we're overdoing it with the current. Let me turn a little more in the same direction. Now it's getting really wide. Now look how it's tracing this wider path here. It's just not the nice narrow dip we saw anymore. So we're overdoing it in terms of canceling the field. And if I keep turning it, the peak just looks terrible, so it's not optimized. But nonetheless, if I go back in the right direction that we sort of found, you can see the peak is getting narrower and narrower again. There we go, something like that. And I'm turning, getting a little even narrower than when I started. Something like that maybe will do. And so when this peak is as narrow as possible, that means we've really canceled the Earth's magnetic field in the vertical sense, and the horizontal sweep, of course, visits a magnetic field at some point that cancels the Earth's magnetic field in the horizontal sense. So this is where the magnetic field would be zero. The other control that I have then is, depending on what I'm doing with the experiment, of course, is I can turn the sweep off by just clicking this knob up to single here, and the sweep stops. But now what I can do is I can just put my hand on the start field for the sweep, and I can totally control that little position right there. So see, I'm totally in control of the sweep position in a manual sense now. Let me reset this. There we go. So I reset it so it goes back to zero. And so here I am sweeping manually, and see there's that peak that we saw, the zero field peak, and if I go down I can totally visit exactly where that peak is zero, like right in there. I can totally nail down exactly what current is required to make zero magnetic field, and I can read that current via the voltage off the voltmeter as described. So that's a very convenient way of identifying peaks on the optical pumping as we go. Let me turn the sweep back on now. So there we go. There's the sweep again. Continuous. Let's keep it going there. And start. There we go. So there's the sweep back again there. And I will reset the starting point back to full counterclockwise so we can sweep over the whole range. And so that's in essence is sort of the optical pumping signal. We're always looking for this zero field to verify that we are in control of the magnetic fields the rubidium atoms are in. And then as we start taking data, if I just turn the RF on, so the RF is now being applied at about 96 kilohertz, you see these two additional peaks occur over here, and those are of course having to do with the individual rubidium isotopes that are in the sample. So this is zero magnetic field. We don't really take any data on this, but we are interested in where these other peaks occur. And as you can see, zero magnetic field, and as the magnetic field increases, these resonances only occur at particular values of that horizontal sweep magnetic field as the experiment goes. And so that in essence is the signal and the equipment for optical pumping.